Yeah, good afternoon. So we are going to look into composite beams and their solutions using equivalent cross sections. Now, these are all we have covered already, and we learned in the last class that this is the how to find neutral axis, right? So it says that uh, y into dA, E into dA, this and this, and then there is a kappa, right? So E1 kappa into E1 into dA was the force sigma x at the location, at a small location, right? At a small location like this. And when you multiply with y, right, and integrate over the range, some range, okay, you get, uh, just give me a minute, just, yeah, sorry, that was HOD. So this is actually moment of this force about this neutral axis. So, okay, that's not the neutral axis, about this neutral axis, right? So the moment of the forces top and bottom of the neutral axis should be equal to 0. That this equation do not take care of whether the material is a single material or the cross section is made up of single material or multiple material. It says that this has to be true when you have a cross section and a beam with the following assumptions that we have made earlier. Okay, this is what we have seen in the last class, and we also saw that the stresses developed in materials are in ratio of their elastic modulus, right? And at the bottom, that's the total rigidity of the material cross section. This is rigidity. We discussed these things in the last class. Today we are going to see how we are going to find the same formulas, when we deal with equivalent cross section. Now, when you do, it is also called transform cross section in many of the books. So I have written that also, but we generally call it as equivalent cross section. When we do equivalent cross section for a given cross section like this, let's say we have been given a material, which is a cross section which is made out of two materials, one here, and the second one is this one. A top one may be stiffer than the second one, or top one may be flexible than the second one. It doesn't matter. Based on the requirement, you will have two different materials with two different, for us, it is two different E, right? E1 and E2. That's what, when we say two different material, we mean that their elastic modulus are different for the materials. What is the constant? So when you try to find an equivalent, you need to find a constant, or you need to find under which conditions you are going to make them equivalent. For example, what are the results that you want to see as an equivalent, right? For example, if I give you a problem and you want to solve that problem in two different methods, the results should come back. So the solution methods are equivalent because your results are same. If you want to do an experiment, you can do that experiment in various formats, but the ultimate goal that you want to measure from that experiment should be same whether you do it in one method or method two. So what are these goals? What are these constants in our objective of this equivalent cross section? So when you make this equivalent cross section, we want to mean is this two cross section, whether you get an equivalent cross section in whatever method you want, method 1, method 2, method 20, they should give you same resistance to the moment that this cross section provides. Okay, by which I mean it should be able to bear the same amount of load that this cross section can hold. Okay, so both of them should provide same moment resisting capacity. That's what is meant here. Okay, and their neutral axis should pass through the same point. Why the neutral axis has to pass through the same point? Because we know that the neutral axis, if it doesn't pass through the same point, my top and bottom shear stresses will differ, because neutral axis, top and bottom shear stresses depends on y from the neutral axis, right? And if your neutral axis changes its position, your y will change its value, and therefore your ultimate capacity of holding maximum shear will change. Similarly, when we say that the neutral axis should pass through the same point, we mean that the force that the top layer provides and the force that the bottom layer provides, even for the equivalent cross section, the moment of those forces above the neutral axis should be 0. So this is the condition that it should provide. So kappa should be there. Oh no, here, right? That's what I shown you here, that the moment should be about the neutral axis of the two forces should be going to 0. Now we can look into few things here, that if you have this expression here, right, this expression can be written, kappa can go to, kappa can be taken to the other side and put it to 0. So we get, since kappa is not 0, we can write that E1 into YdA of the material 1 into N into E2 of YdA. What is N? N is ratio of E1 and E2. Since there are two materials, I can always find a ratio which is E2 by E1, and this ratio N is called modular ratio, or it is also called sometimes transformation ratio. Okay, once you have that, you can replace E2 with NE1, right? And if you do that now, if you see, this guy is made up of one single material because both are with E1. I don't have E2 anymore. So once I replace that, I am making an E1. So this is an equivalent expression of this, right? Equivalent expressions. Okay, why it's called modular ratio? Because it's a ratio of two modulus. That's why it's called modular ratio. Now I can write them as, I can take E out of the expression completely. And if I take E out of the expression, I have this guy left out in between, is YdA plus NYdA equal to 0. Now you see, now in this expression, there is no material at all. It's a completely a geometric expression, right? This is, okay, this is same as here, is a geometric expression. It is not, it doesn't have any material into it. It's independent of material. Therefore, I have converted already my system to an equivalent system where material is of same modulistic modulus. Now this n is there. You see, this n is there, which I can write as NdA. Okay, because my neutral axis has to go through the same point. So what I'm doing, I'm just changing the area. All right. Now when I change this area, I can change this area in two ways. We'll look into this. This area change NdA can be made in two ways, right? I can write it here. So this is written as over 1 YdA plus over 2 y into NdA. Now NdA can be obtained in two ways, right? Two simple ways. You can assume any complicated ways you want, but two simple ways. One is change y, keeping width same of the second material. Two is change width, keeping thickness of the second material same. All right. Now, which one should we choose? I can. So what I mean here is, this is the area that I need to transform. Second area I'm transforming because it is multiplied with the second part of the material. So this material I'm going to change. I can change it in two ways. First is I can keep keep this B same, and I can increase the width so that the area becomes same, N into dA. Okay. So the total area should be n times this area, which I can find out. Otherwise, what I can do is I can keep this y constant. I can change the width, which has been shown here, right? So these are the two ways. First is if you have a rectangular cross section with, let's say, two different materials. Let's say this part is a different material. Then I can change it into like this of same material, right? So I can make it as NB and this remains same. Let's say this is D1 here. Or I can do something like this. I can make B same, but this distance I can make ND1, right? But B is same. Now this is the correct way of doing. This is not the correct way of doing. Why? Now both of them are made up of same material. So let me paint them also. So let's say this is this material and this guy is this material. Now both of them are same material. Why not? Because I want my neutral axis to remain in the same position, and neutral axis depends on y. So I don't want to change y. I want to keep the y same, so the neutral axis remain in the same position. And secondly, my stresses also remain same because that depends on the distance between neutral axis and the top layer or the bottom layer. Okay, so this is not considered, and this is considered. Next thing is, you may ask me, sir, why I am changing equivalent, why I'm making an equivalent section of 2, why can't we make it for 1? Yes, you can do it. You follow the same thing. You can make of, instead of making like this big, you can make it also something like this. You can reduce, your top material, and both can be of your, let's say this is the color, right? So both can be of your second material type. Okay, in that case you don't multiply with n, you divide with n. That is also is doable. It's very much doable. You can do that. Only thing is, I will always suggest to always multiply it, because division always gives rise to decimal values, and if it gives rise to decimal values, it becomes very difficult for you to carry on the calculations. But if you multiply it with n value, that means the model ratio, it will always be helpful to you, because in that case you don't end up having decimal values and calculations become easier. Okay, and you do not end up in approximations. So that's what is called equivalent section. This is your equivalent section. And you can see the area is now n into B2 into this, right? So area is now multiplied with n. Area now is multiplied with n, as you can see, as was required in this expression. The same thing we did here also. We multiplied with n. Here also we multiply. Both will, in both the cases, it will result in same change. Here are a few things that we discussed just now. The method, what you want to do, you can change area 1 or you can change area 2, and then you have to change with respect to the modular ratio. And there is a simple example that is given, that if your modular ratio is 10, what happens? This is what we discussed just now. Now, moment curvature relation, we have changed an equivalent section. We got an equivalent section. Now, from this equivalent section, we don't remember anymore the original configuration, right? Original cross section. We only remember the equivalent cross section. How do you find your stresses from this equivalent cross section? That should be the objective, and it should lead me to a very simple solution, right? Otherwise, why should I go for equivalent cross section, right? So this is my equivalent cross section. This is my equivalent cross section. The original cross section has changed to a hat type of cross section, with the bottom layer is n into B2. Right? Originally it was B2, now it is N into B2. Now this guy is made up of only single material, right? This is made up of only E1. In both the cases, it is E1, here also E1. So now it's a beam cross section which is made up of single material. And you know how to find stresses for a beam cross section made up of single material, right? Its stresses will be given by this relation. Sigma x equal to E1 into kappa into y, because it's a single material. And therefore you can find all the stresses at all points here, 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 here. Okay, you can find it. You know sigma x is equal to m y by I. There is a minus sign to take care of compression on the top and tension in the bottom. So now that can be expanded. So this is my stress, and now this stress I can add. I can separate it. In a whole area I can separate into area 1 and area 2. So this is area 1, this is area 2, and once I separate them into area 1 and area 2, I'm just going back to my expressions. Separate into area 1 and area 2, we can write this as E1 kappa y1 square dA, E2 kappa, again E1 kappa y d square, y square dA. Now this dA, if you see, this dA is the dA of the transformed cross section, right? So that is nothing but N into B into dA, B2 in our case, N into B2 into dA, right? And therefore you can take this A B out. In that case, it will go back to its previous configuration, right? If you take that N out, you can multiply that N with E1 and it goes back to E2. N into E1 is E2. All right. So once you do that, you get your, see, we got back our expressions. Kappa into E1. So this is your total rigidity of the material. So this is called moment curvature relationship. It was same as we got in our last class. Now, how do you find, so how do you find your, okay, let's get back here now. So now I can find my stresses using these relations, right? Sigma 1 equal to my by I. And one thing I want to say here is this expression that we got, can also be written as m equal to kappa into E1 into I1 as n I2. Yeah, can be written, right? We can write that in this format also. And if we write in that format, you can see what I'm doing is I'm again having the same material, only one material here, and this is the I of the transform coordinate, moment of inertia of the transform, sorry, not coordinate, transform cross section. Okay, and that is called IT. This guy is called IT, total moment of area. So that you can now write sigma x equal to my by IT. So sigma x is nothing but same as what we have done in the last class. Now, how do you find sigma at various cross sections? Right, this, and this. We know that for equivalent cross section, we can definitely find it using the relation that we just developed here, sigma equal to my by IT. But wow, how do you go back to your original cross section with original materials and find the stresses? So the material 1 was my earlier material. It was the same material even in the equivalent cross section, and therefore for material 1, the stresses will not change. This is what I wrote here. For material 1, the stresses will not change. It will remain as you find it in the equivalent cross section. But for material 2, it has to change because material 2 is different from your equivalent cross section, right? And that is why you find it like this. So sigma 2 is also equal to m into y into it into n here. So you just multiply with n value to find the stresses in the second material. So that's the formula that comes out to be at the end. And these are the formulas we already know from our last class. So let's do a simple problem. Yeah, let us just do a simple problem. It will take another 2-3 minutes, so we'll stop recording after that. Let's do a simple problem. So this is the problem we took in the last class, if you remember. It was a wooden member, rectangular wooden cross section, and at the bottom there was a material made up of steel, which has been metallic material, which has been attached firmly with the wooden material. And we have been asked to find stresses along A, B, and C points. How do you do that? First thing is we need to find modular ratio. First job one, is to uh, find your equivalent cross section. Determine the equivalent cross section. So for that we need modular ratio. So we just divide E2 by E1 because E2 is higher value. So I'll get a multiplication factor which is a 20. Okay. And now what I'm going to do is when I'm multiplying with E2 by E1, I'm going to change my material cross section which is made up of steel into wood. So what I'm doing, I'm changing my material steel which was here into wood now. So I'll just multiply the width of the section into 20. So earlier the width was 4 inches. Now I multiply with 20, it becomes 80 inches. So this is my equivalent cross section now. All right, it's almost like a larger web T section, right? So this is my equivalent cross section. Okay, the width has changed from 4 inches to 20 inches. So now my equivalent cross section is different. It has 4 inches in the top, then which is made up of wood, and then bottom also now it's made up of wood and has a width of 80 inches. Okay, we need to now find what next part is to find neutral axis, right? This is my step 2 to find neutral axis, and my step 3 is to find total I. Is my step 3. How to find neutral axis? You know how to find neutral axis for this cross section. You find neutral area of this multiply with the centroid plus area of this multiply with the centroid divided by the total area. That is what is done here. So this is your 6 inches. So this is the area, 4 inches into 6 inches into 3 inches is y bar. Okay, plus this 6.5 inch because this is 6 and there will be 0.25 here. So 6.25 inches is y bar, and then the area is 80 into 0.5. Remember, this is now 80, not 4. Okay, and that divided by the total area. So that comes out to 5.031, same as what we got in the earlier last class. And therefore H2 also you can find out from here. Now how do you find total I? Total I is the total I of the cross section. You know the cross section now. So IT is going to be 1 by 12 BD cube plus the A into D square. This is A into D square or D bar square. And here also 1 by 12 BD cube of the changed profile. So that is 80 is the B and D is 0.5. So that's what you get. So finally you get this, and this is also same as what we got in the last time. So now getting sigma values are easy. We found step 4 is find stresses. At various points, right? At various locations. At various locations. Okay. How do you do it? We know the formula is sigma equal to my by I with a minus sign, right? And in the material 1, in material 1, and that same will be sigma equal to minus m y by I into n in material 2, right? So sigma 1a is in the material 1. So if my cross section is like this, and I have 2 different materials, this is what I had, right? 2 different materials. This is my A point, if you remember, this is my C point, and that's my B point. So A is in material 1, C is in both material 1 and material 2, just above and below, and B is in material 2. Okay, so A is in material 1, that comes out with my by IT, and then what is IT? Where is IT gone? You are 231.3, and that comes out to be 1310 psi. Similarly, sigma 2b, that means here is in the material 2, and therefore we have to multiply with n, and that comes out to be, if you put the values, you get 7260. What happens if you don't multiply with n? If you don't multiply with n, then it will be similar to the stress that a wood will carry if wood has been attached in the material 2 portion. Okay, and that's why it is not right to not multiply with n. And then sigma c, c will be both 1 and 2, so sigma 1c is in the material 1, is you don't have to multiply with n, and that comes out to be 251, whereas sigma 2c, you just multiply with n, you get 2050. So this is what we have seen in the last last class also. The results are given for the last class. You see the values do match with what we have found using equivalent cross-section method. All right, now it's up to you to decide which one is easier. If you have many things, many materials, and they are not so properly aligned, they are distributed randomly, in that case your equivalent method is much faster and easier than the other method. You just need to know how much is the volume fraction of the second material, and then you can convert that volume into an equivalent volume of one of the material and solve the problem, right? But if you want to do it analytically, it's not going to be so easy if you have many of these materials. Now you need to draw, finally your solution is not complete unless you draw your stress and strain curves. Okay, so your stress curve is going to look like this. It is tensile at the bottom, and then it is going to go linearly, and then there will be a change here, and then it will go 0 at the neutral axis. Oh, did not draw properly. Yeah, 0 at the neutral axis, and then this. So this is sigma A, this is sigma C, sigma 1C, this is 1A, this is sigma 2C, and this is sigma 2B. And the strain is going to be the same. Right, this is going to be your strain. Strain will not have any change because strain doesn't depend on E. It's a geometric property. All right, so that's how you have to finish your diagram, and you can give proper arrows if you want. This is tensile and this is compressive. It's up to you how to draw it. This is compression. That's the complete picture of the problem. Okay, and that's what we got in the last class also. So this is one of the method that is very simple and very easy to do. So please solve a few problems. Also solve a problem which is made up of like this. I gave in the last class with two materials like this. This is material 2 here. This is also material 2 here. Okay. So as you know, the neutral axis will definitely pass through the center because you don't have to do a separate calculation for this. This is material 2, E2. This is your E2, and that's your E1. So this, its equivalent cross section will look like this. If E2 is higher, larger, then it will look like this. Not in scale, not in scale. So this is E1. Now this is also E1. This is also E1. Only thing, this guy has changed. It was, let's say, B. It has changed to B into E2 by E1. Okay. Other things remain same. T1, T1, T2. Okay. Now this looks like an I section, an exaggerated I section, and you know how to solve I section, and you can solve all the points where you need So the critical points, always remember, are the points which you need to show your values. This is 1 point, this is 1 point. Similarly, this is 1 point, this is 1 point, this is 1 point, this is 1 point. All these points you have to show your stresses. Okay, and you will see stress jumps along this line, and there will be a stress jump along this line, right? But strain will not jump; it will be 0 at the neutral axis. With that, I'll stop recording. If you have questions, I'll be happy to answer.